Okay, so let me start where we left off. So give a think for a start with the assignment, the whole rule for assignment. So there are, as I said, there are two ways to express the meaning of an assignment statement in terms as whole triple. One that defines the weakest precondition, the other one that defines the strongest postcondition. So this is one that given a postcondition, it defines the weakest precondition that satisfies this whole triple. So when you do this, what exactly is it saying? If P, a predicate P is to be true on the values of the variables in the post state, that is the state that you get after executing the assignment statement, then what it's saying is P must already have been true, must be true on the value of E in the evaluated in the pre-state. Okay, and why? Because this is the case because what this assignment statement does is it changes only X. There is no variable except X is changed. That is an assumption, which means that evaluation of E, we're assuming in our programming language, does not have any side effect on any of the variables other than the value of that being assigned to X. The value of E as evaluated in the pre-state gets assigned to X. The other important thing to notice, the E itself, the expression, is evaluated in the valuation that exists in the pre-state. Okay, and it's based on those two, meaning of an assignment statement that this predicate, so where E X here is exactly what you get by replacing in the description, that is the formula that defines the predicate P, every instance of the variable X by the expression E as is. Yes, isn't this backward? Yes, it is backward, but it is quite simple. I mean, you see, all it requires is, it's very neat because all it requires for you to derive the precondition, and the weakest precondition is just a substitution of the expression E for the variable. Okay, it defines the weakest precondition. It is the weakest precondition for P because if there was some other Q that was weaker than this, then there must have been some value in the pre-state, which after that does not satisfy this P of E, but after execution, it ends up satisfying P on the value that X gets assigned. But that cannot happen because this E, that means then that that value couldn't have been produced by this evaluation of E, which is what the meaning of X as being assigned E actually means. So that's why it couldn't be that if that is the case, then there's some other value that is being assigned to X. So that is a contradiction. That's why this gives the weakest precondition. Okay. Now here are some examples. So X, if you have the assignment statement X is equal to X plus 1, and your postcondition is X is greater than 0, then what it says, what this says is, as per this assignment rule, what the precondition, the weakest precondition is P with X being replaced by whatever the expression E, in this case X plus 1 is, and that says x plus 1 must be greater than 0, which is equivalent to x is greater than or equal to 0. Okay, so is that clear? Any questions here? Okay. Now, so let's I kind of rushed through the version of of the assignment rule that computes that defines the the strongest post condition by pushing the given precondition forward. Okay, so here are some I think some people suggested why it is not there. So I kind of added these things. So some of the false intuitions, you would think that if you started with some state in which predicate P is true, after X is assigned the value that you get of some expression E, which can have variables in X. Okay, one is, maybe you can say, oh, that predicate should be true, the post condition be such that if you just substituting X with E. See, that creates nonsensical Haute triples. As you can see from this example, you start with X is equal to 0. Okay, the predicate X is equal to 0. If X is assigned to 1, if you just simply replace P, the X in P by 1, then it becomes 1 is equal to 0. Okay, so that cannot be the post condition. See here, so the reason that you have to be careful when defining these things is because here is a predicate. So the predicate itself, or the formula that defines the predicate, only uses the variables. Okay, in the post state, it uses it uses the same set of variables. Okay, whereas the assignment, the semantics of assignment assumes that the expression will have to be evaluated in the as per the evaluation in the pre-state that satisfies the predicate P. Therefore, what you want is when you push this forward, you want, so that distinction between the variables have to be made. So another thing is, that X will get assigned value E. So you would think that, okay, in the post condition, X must be equal to E. And you also know that, P, you're starting with the, a state in which P holds good. So only those values need to be carried through. Therefore, you would think that the strongest post condition going forward would be P and X is equal to E. You see, that also does not creates anomalous situations. So for example, we start with X is equal to 5 and X assignment statements, especially the case when we have the same variable that is being assigned as part of the expression. Then what you end up getting is, by just saying X is equal to E, you will make this nonsensical statement X is equal to X plus 1, okay, which can never be, which can never be true. But what you really want is, when you do this in a forward direction, you will have to distinguish between what the values that satisfy the values of the variables in the pre-state. That things. What you really want to state is, my post condition is such that X is equal to whatever the value E evaluates to, assuming that the valuations for the variables, for all the variables that appear in the expression E are as per the pre-state, such that P gets the values of X such that P is true in the pre-state. That's how you will have to state. Okay, and that's why the proper way, or one way to do it is, so if you start with P is a precondition with defined by the predicate P, then after you evaluate this, what you need to have is that there are two things. Okay, so one is that whatever that X gets assigned should be the value of E, such that V is, X is replaced by some value V, such that the precondition P is true on that V. Okay, so those are the kinds for every value that such that there is such that P is true. Then for those things X could take those values, and this is how is a thing that has to be stated. So that's why stating it as this moving, pushing, propagating the predicate forward is a little bit, bit harder than computing the weakest precondition by pushing the predicate backwards. Okay, so let's maybe you're still scratching your head as to why how this existential quantification will actually work. So let's take a few examples, okay, that I will illustrate, and then I will also show you a lot of some more examples that makes you comfortable in defining set of states in terms of existential quantification. Okay, so let's take this simple example, same thing that we saw earlier, where you start with a pre-state in which X is equal to 5, and after you assign X is equal to X plus 1, what this thing is saying, your strongest postcondition is defined by this formula, which says there exists a V such that X is equal to such that P, which in this case is X is equal to 5, should be true, and then what the value of X for every such V that satisfies P, the value of X allowed, permitted, is V plus 1. So when can this be true? For example, there exists a Vx is equal to 5. Here in this case, there's only one value, correct? Which is?
Sorry, sir, I have a doubt about this. So it should be there exists V such that P of V is true, right?
Yeah, P of V is true, correct. This is to be 5 is equal to such that there exists a V such that V is equal to 5. I'm sorry. This has to be V is equal to 5. It should not be X. Good observation. So there exists a V such that V is equal to 5, and then X is equal to V plus 1. Okay. What is that V in this case? That V
5
is 5, correct? Because that's the only value of X that can satisfy P in the pre-state. So then, so the only, the state that satisfies this includes exactly the state in which X can take 6. Okay, so that's the intuition. Yeah. Okay. So another example. So here is a case where you start with, your pre-state is anything that where X is greater than or equal to Y. Okay, let's assume that here X is integers. Okay, then after X is equal to X plus 1, once again I made the same mistake. The X here in the post condition has to be this X here. The first instance of X has to be V. Okay, so it's saying that the post state and the strongest of that, the one that is strongest is any V such that P of V is true, and for every such V, X has to be V plus 1. So if you now replaced so this would be, see, so here you'll have to use a trick to eliminate that existential quantification. What this is really saying is, suppose there is some X naught such that some arbitrary X naught, okay? So you could eliminate, one way of eliminating this exists V is to substitute for V some x naught, which can be any integer, such that x naught is greater than or equal to y. And for every such x naught, x can take the value x naught, that x naught plus 1. Okay. So this also takes care of having propagating this p, instantiated version of p to the post condition, takes care of another like a tricky situation. What if there is no value? P is false. Okay, for example. Okay, there's no such value that can take. Then, as you know, if the precondition is false, the strongest post condition has to be false, because if there's no such value, then the strongest post condition has to be false. Okay, so this will take care of that. So all this is saying is, it is x can take those values such v plus 1, for which p is p on that value is true. There's no such value. Obviously, this condition x not greater than or equal to y will itself be false. Okay, so it takes care of both of those things by the situation where there may not be any value such that p is true in the pre-state, as well as the the requirement that E has to be evaluated in the pre-state, and that's why so you can do this. So it takes care of both of those situations. Okay, so so in order to so as you can see then that this this post condition that you have derived when expressed in terms of x naught really satisfies the post condition that you would expect to be true after the strongest post condition, which is x would be greater than y. Okay. So as you can see, so this existential quantification is a neat trick that you can use to do. You can use to push the predicate forward to get the strongest post condition in your proof, but it has the disadvantage of introducing existential quantification, which, as you can see, can be eliminated by introducing new variables, okay, which can take unconstrained variables, like I have done here. But in doing this, you will have to be careful of, in the way that you do. So, so I will give a version of this. I will show you a version in the next couple of slides, where you could, a version in which the existential quantification doesn't have to be there. It is kind of automatically eliminated using the kind of trick that I've used in the to illustrate in the second example. But before I do this, you you may, I want to go through some examples to acquaint you with what it means to use predicates to define sets of states, especially when you have existential quantifier. I hope you got some intuition. So if you still have questions, wait until I go through the next slide, in which I show you a lot of examples of using predicates with possibly including using existential quantification to define or to characterize set of states. Okay. Some basic, sets of states as predicates. Okay, this is small diversion. After that, I will get back to the forward assignment rule. Okay, maybe Diganta, you have done, and you've seen this, might have seen this in tutorial, and you're probably already familiar with this, but let's use it as a useful recap. So when you have a predicate px, say for example, x is less than or equal to 0, so it defines this set, the set of values, say x is ranging over an integer. So let's assume. So it has all the integers such that x is less than or equal to. So that is the, so P is the characteristic function that defines the set of values. So it includes, the set includes every value and exactly those values for which that predicate is true on that value. Similarly, if Qx is defined as x greater than 5, it includes every integer such that is greater than 5. Now, so in this formalism, when you express sets as predicates, this junction can be used to take the union of the two union of the states represented by the two arguments to this junction, and conjunction will have the meaning of intersection. So for example, if you had px and qx, px or qx, then it'll denote exactly this the set of states that you get by taking the union of A and B, where A denotes P is the set denoted by P, and B is the set denoted by Q. Similarly, if you take conjunction, can then be will denote the intersection. In this case, if P and Q are defined as above, A intersection B will be the empty set, because the intersection of these two sets, A and B, is empty. Okay. Now, what happens when you take the existential quantifier? So, existential quantifier really denotes what I call as disjunctive abstraction. To see, and that is the notion that is actually being used when you define the assignment rule in the forward direction. Okay, so let's see, what do I mean by this? Okay, so take, say, for example, this binary relation Rxy, which is defined as x greater than 1. What does this predicate denote? It is those pairs of numbers, natural numbers. Say I'm defining the domain as natural numbers, I and j, such that I is greater than j. So that means that it includes, this exactly characterizes this set of tuples, pairs that I've shown here. So in every tuple, the pair, that the first component has to be greater than the second component. Now, when I take the existential abstraction, say there exists an Rxy, what does this predicate denote? Can anybody guess? Obviously, one hint that I've already given, when you do there exists an Rxy, that is a predicate over a single variable. Okay, so that it's there. That's why I mean it is an abstraction in the sense it constructs a predicate from a where it eliminates this one of the variables in the original predicate. So what does this denote?
The set of natural numbers.
See, actually, no. So what exactly it denotes is, so one way to define existential is, what it says is, okay, there exists an x. Okay, what does that mean? So there exists some natural number. So this will be true for every x, for any given y, for any arbitrary y, it will be true. This formula will be true for every x. Actually, natural, that is not exactly correct, okay, as you will see. So one way to, when will this be true? So as long as there is an x such that Rxy is true. So this you could view it as taking the disjunction, okay? If it is true for x is equal to 0, then, for any y, if it is true for x is equal to 0, then you have to include that y. If it is true, it's not true for x is equal to 0, if it's true for some y, some x. So it is as though you're taking the disjunction of this entire, okay, it's an infinite disjunction, since here x is ranging over the set of all natural numbers, it is defined by all those y for which either it is R0 is true, or R1 is true, R2 is true, and so on. Okay. So, R0y, there is no y for which R0y can be true. Why? Because R0y says that x must be greater than 1. So 0 can never be greater than any natural number. So this includes, this includes the set of all natural numbers except for 0. Okay? So this should be, so it is characterized by y greater than 0. There's a mistake here. This x should be y. Okay? So it is true for all, that's the set that for which this is exactly true. So it is characterized by y greater than 0. So that's why I call taking existential quantification is equivalent to taking a disjunction over all the values, that instantiating that x over all the values. Now, what someone said of, that includes natural number. If, for example, if you eliminated y, okay, if you took the, if you derived S1 of x by existentially abstracting the, quantifying the second thing, then you have this formula, existential quantification will be exactly true, will be equivalent to this infinite disjunction, which you get by plugging all possible values that x can take. Okay, I'm sorry, y can take. So that is our x0 or our x1. It includes all those x's for which this disjunction is true, and you can see that this is, of course, this Rx0 is false, okay, but Rx1 will be will be true for exactly when x is equal to 1. Rx2 will be true for 0 and 1, and since taking disjunction is like equivalent to taking the union, it will be unioning 0 with 0, 1, 0, 1, 2, and so on. Therefore, this is exactly equal to the set of all natural numbers, which is denoted by true. Okay? So this is something that you will have to be, you see, taking existential quantification is like, deriving a predicate with fewer variables, and it is like then taking the union of instantiating that variable which is being existentially quantified over all possible values that it can take in that domain. Is that clear? Questions?
Yes, sir. So I actually think that shouldn't it be the opposite? Like, for
maybe I
instance,
made a mistake. Okay, so let's see. So why I'm saying.
So yeah, so in S2 of y, if y is equal to 0, then R1 of y will be true, right? Because 1 is greater than 0.
You're right, man. You're right. Okay. So it should be the other way around. Yeah. Okay. This should be all nat, and this will be 1, 2, and 3. Yeah. Yeah, that's correct.
Yeah.
Yeah. So 0. Yeah. No. I think I'm still right. Okay. So 0. So you should be asking the question what? So what values? No, I think I'm still correct. So for what values of y can R0y be true? So can y be true for 1? You're right. Okay. Yeah. So those y's for which 1 can be greater than. You're right. Okay. Yes. So this cannot be true for 0. So one is, the values of y for which R1 y is true is exactly 0. Correct? Yeah. 2 can be greater than 0 and 1. Okay. So correct. So this has to be NAT. Okay. And this has to be y greater than 0. Okay. I'm sorry. Yeah, good. So who pointed that thing out? Good. Thank you. Yeah. So this should be y greater than 0. I mean, yeah, the way to convince yourself is to see what values of y for which any of these things is true. So you're right. This has to be NAT, and this has to be all but 0. Good. Good for pointing that thing out. Yeah. So any other questions? And yeah. So what you saw as post was, was this. Okay, if you had R, if there was, your precondition was Rx comma y. Then your post condition, it will be all those x's. If you're assigning x to, post condition is used by doing this kind of a thing. Okay, so, and this is the way that you should interpret, that thing, that if you had x is equal to x plus 1 or something, then you would have, all those y such that you're exactly, there must be some value of v for which r of v of y will be true, and you will have x is equal to v plus 1. Okay, so that's that will be the, and y will be the could be anything. So that's how that is the intuition for defining the thing, and then you can check this out, and then you will exactly get x is greater than y plus 1. So this is one way to eliminate this existential quantification variable, is by introducing a new variable x naught. Okay, and then saying that your post condition should be r x naught y. Okay, and x is equal to x naught plus 1, where x naught is some brand new variable, okay, which can, brand new variable which is unconstrained, which can take any integers. Okay, so one way to state this, an equivalent way to, instead of using the existing quantification, one way you can do that is by introducing a new variable x naught, which denotes the initial the value that x can take in the pre-state, and use that to express to instantiate the existential quantifier with, and that's what, and then you can then eliminate that. So if since x naught can take any arbitrary value, you get the effect of enumerating or including in the post state every value that x naught can actually take. So so you get you have the same effect, and this is what we will now use to define a version of the forward rule for assignment without using the existential quantifier. So then what I do is, so first, if I'm starting with the precondition p of x, I'm going to kind of enhance that by adding a new equality which defines the initial value that x may have in the pre-state, and px. Then after this assignment statement, the post condition. So the values that e can take are exactly what you get by replacing x with x naught, the value that x takes, and it has to be restricted to those x naught that you use to evaluate e should be restricted to exactly those values on which p is true, because you're starting with the precondition p. Okay, and this defines. And here, the important thing to observe is that x naught has to be a new variable that does not exist in p or in E. It has to be, yes, okay, and that's what how you can actually define. So you will create here. I'm creating a new variable. Of course, I've always created a new variable to denote the value of x that is being assigned in the pre-state, and then in order to, then I'm defining a new variable to denote the value that the new value that x1, the variable x takes, and then I'm equating that to x. Okay, because I want to because all our predicates have to be defined, whether it's the pre or the post, on the they'll have to be defined on the program variables that are being used. So these new variables x0 and x1 are something which do not clash. That's the most important, clash with any of the program variables. Okay, so that is what you will have to keep in mind, and they can be any new variable, but it's range over the same type as x. Okay, now. So here is a version. It's a version of the same thing when you have multiple variables. Here I have illustrated it for a single variable. When you have multiple variables, you will have to introduce multiple, the initial values to denote the values that each variable can take in the pre-state, and then what you will do is then you will have to instantiate in the post state p with the value, the initial value, only for the variable that is being assigned, because all the rest can be x, because this only y is getting changed. Okay, whichever is getting changed, being assigned by this assignment value, that is the one for which you will instantiate p in the post state. All the rest you will keep as is. Okay, I'm sorry, there is one thing that is missing here. You will have to carry forward y is equal to y naught, y is equal to y naught also. There's a mistake here. So assume that it has to be, it has to be whatever, instead of p, this should be pre-con. Okay. So what you have to instantiate, you enhance this with these equalities, and this has to be a pre-con, okay? This instantiation has to be on this enhanced thing, okay? That's a mistake that I made. So I'll tell you exactly what I wanted, okay? Forward rule, where do I have? Yeah, so what I meant was this one, okay? Yeah, what I meant there was, see, you enhance this with pre-con. Okay, where do I have? I have a version here, which, okay. So here it is. So there's a mistake here. This is the exact thing that I want. If you have multiple variables, suppose you have p, x, y, lots of variables, then you assign x is equal to e x y z. What should be is, first step is you create a new precondition which adds initial values, okay? The values, new values that x, y, each of these variables can take, okay, dot, 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 okay, to the predicate. So you add, you create a new precon, okay, by adding this to thing. You do this. In this case, x is being assigned, so you will instantiate that by keeping all the rest the same, okay? I'm sorry, this is just, that's x, okay? And then what you do is, in the post condition, you will plug in x naught, okay, whichever variable, the initial value for that variable, which is x naught, and keep the rest the same. Therefore, when you do this, what you have is, if you had only two variables in your predicate x and y, then you will have x is equal to x naught, y is equal to y naught, okay? And then when you plug in, in this case, y is being assigned. Therefore, you plug in y naught. So one of that will become true. So x is equal to x naught will have to be carried over here, okay? So what this should, in this case, should look like, what I have in the slide should be something like this. X is equal to x naught, and you will have y is equal to y naught, okay? And what you have is y is being assigned e of x comma y. You have some precondition p of x comma y. After this, what you have is you have to plug in, since y is the one that is being assigned, you have to plug in y naught into this entire thing. When you did that, this simplifies to true, but all the rest of the value will be carried over, okay? So you will have p of x comma y naught, and you have to assert y1 is equal to, all the rest is correct there, okay? And you will assign y is equal to y1. I mean, that the last assignment is just being done since we want to express the predicate here in terms of x and y. We want to define, always keep our predicates, have x and y variables in there. So, but you will have, that's the mistake I made here. So we have to carry. So the instantiation will be on the entire pre-con as I have denoted, as I've specified here. Okay, enhanced.
Sir, but here too, in some sense, we are using an existential quantifier on the precondition, right?
No, these are two equivalent ways of stating that. What I have, yeah, you are using, if you want to use existential quantification, the existential quantification appears only in the post condition, not in the precondition, but it is being, existentially quantified over the precondition. Yes, this P here should be pre-con, okay? That is the mistake that I have made. But a pre-con is this entire formula, okay? Is that what your question is? No. When you are expressing in terms of existential quantification, you don't have these extra equalities, okay? So this is a version of describing the forward rule by, in such a way that you don't, existential quantification is already eliminated, okay? These two are two equivalent ways of doing it.
Yeah.
Okay, so here is an example. Okay, if you had x is equal to 5, x is equal to x plus 1, then your post condition will first, it is like introducing x is equal to x naught, adding a new thing for every variable. In this case, there's only one variable, therefore, and x is equal to x naught. And you have x is equal to x5, and then you have, in this case, what you will be instantiating it is with, x can be, so x naught is equal to 5. So you're instantiating this entire precon on x naught, which is what I'm doing here. Okay. But when you instantiate that with x naught, you get x naught is equal to 5. X naught is equal to x naught simplifies to true. That's why I am not showing that. And then you have this, this equality for the new value, okay? Where I'm creating a new time-stamped thing. So saying x1, I'm creating a new variable in the post, predicate to denote the new value, okay? And that you can get by just so that it is unique. You can create a unique timestamp for that, and then you equate x is equal to x1, and you will see that this entire thing, this whole thing, will imply x is equal to x6. All you need is just a set of equality substitution. X naught is equal to 5, x0 is equal to x naught plus 1, and therefore, and x is equal to x1, therefore, x is equal to 6. Okay. So that is what happens. Now, if you have two variables, so this is a thing where you have two variables, x and y, in the predicate, but only one variable, one of the variables is being assigned. So in this case, your precon will be x is equal to x naught and y is equal to y naught, because you have to keep track of the initial value for both x and y. And then you instantiate this whole thing, entire precondition, with the initial value of the variable that is being assigned, which in this case is x. So when I instantiate that, x is equal to x naught simplifies to true. Therefore, y is equal to y naught is carried over x naught. Then you get x naught greater than or equal to y. That is the result of instantiating this one. And then you create a new variable to hold the new value. Okay, and then you assign that to x equal to x1. And the reason that you carry over these things is because when you see, you might have to repeatedly apply these things when you propagate over several sequence of assignments, and then it becomes, then you will need to carry this thing through. Okay, so that's what the forward rule is. Okay, so any questions here? So I will show you more examples. Okay, so it should be hopefully clear after those examples. But any questions here? Okay, so we already saw this. So these are the basic rule, other than the skip one, that define the whole triple for the atomic commands, for the basic commands. All the rest are built using inference rules. I mean, you construct the whole triple for a program from its given the whole triples, valid whole triples for its subcomponents. Okay, so if a program is consists of two commands Q, subprograms Q and S that are composed using the sequential command, then if you get if P Q R, this triple holds, and when you take R and then push it through S, then you get T. Then this is, then when you compose for the program Q composed with S, sequentially composed with S, you get P and T. So this is the result. If you have two cards, okay, so there are two assignment statements or two programs, and then if you already kind of established that the post condition for PQR holds good, then because this takes care of the thing that whatever S is executed in the state that you get as a results as a that you get as a result of executing the first piece of code, and that's what this thing is saying. Okay, now this is the forward version of the thing. You can so we can also have a backward versions. If you start with the same post condition, then you can also have a backward condition in which if you start with some post condition. Anyway, so yeah, I will show you proofs. Okay, so after I define these rules. Okay, I think if you see this can be used for pushing the same precondition forward. Okay, through the programs. So if you want to push it backwards, then you'll have to take T to some R1, and the same T should be pushed to R2, R2, and then you will get R2. In other words, you will have, if you had a P here in place of T, then you will get two other things. Okay, so you can see a version of this this thing, so which will look like as follows here. Okay, the composition rule backwards will be, if you had I think it'll be this. Yeah, if from T you get P1 and what I'm saying, yeah. So you have to push first S, that you get R, and then no, I'm sorry, it's the same version applies. What I'm saying, yeah. So you can either do it from P, you go to R, and then R to T, or you can push T. So the same composition rule, what I was thinking. Okay, so you can also use it backwards. From T, you push it back and to get R. Then from R, you have to push it through Q to get P, and that's all. That's all this thing is saying. Yeah, I got. Yeah, so this can be used both in the backward fashion or in the forward fashion. So I wasn't thinking. So you can either start with T to get R, and then you have to use that R to push it through Q to get P, and that's all this thing is saying. Or you can use the forward way of doing it. So by starting with P as well. Now these consequence anything rule are used whenever you push P through a piece of code to get R, but you may have your precondition that is weak, that is stronger than P. If P prime implies P, then you can also conclude P prime. This is usually done whenever you push backwards a predicate R, a post condition, to get your weakest precondition, but your starting assumption itself is something stronger. Then you will have to. Then you might have to show that P prime, that your starting assumption indeed implies P. Okay, because your starting assumption might be something stronger than P. Then you will have to show that P prime implies P. Similarly, if you do P, you're doing a forward strategy to push P to get strongest post condition R by pushing P through Q, but your post condition eventually that you want to prove is something weaker than say R prime, then you need to all you need to do is to take this strongest post condition and prove an implication. If you post the real post condition that you have to exit condition after you execute this program is something that is weaker than R, then you will have to, that's when you use this rule. R implies R prime to get P, Q, R prime. Okay. Yeah. So with these rules, now we can see how you can construct proofs. Okay. So I will use this to so here is a swap program. Do you want me to make it slightly bigger, or is this big enough?
I can see it fine.
Okay. So you have, so you have this is a program that, swaps the values in X and Y by using a temporary variable Z, okay, Z. And what you want to prove is that if X is equal to X naught and Y is equal to Y naught at the beginning, then you have X is equal to, X will have Y naught, which was the value of Y, initial value of Y, and Y is equal to X naught. So what you do is, so I'm here using the backward assignment rule to push this post predicate all the way back, and for which I'll have to start with this. So by using the assignment rule I first start with this. I will first push this through this. So this entire program is a composition of two things: the C2, command C2, and the command C1, C1, which itself is a sequential composition of two things, and therefore I will do this. Okay, so I'll first start by pushing this predicate across Y is equal to Z. So that is done by applying the assignment rule, backward assignment rule on C2, on this, which says just replace every occurrence of so here, so you have to replace Y, because Y is being assigned. So Y will be replaced by Z. Okay, so that's what this I'm getting by using this backward assignment rule. So in this predicate, I am replacing X by, Y by the expression E, which in this case is Z. Okay. Similarly, I do, once I do that, then I take this thing, okay, whatever I have pushed it, okay. Now this thing, I'm going to push it back via, on these two, okay, these two statements. Similarly, I take, for example, this one I'm using here. That's the predicate that I'm using here to push it across X is equal to Y, which is the C12 command, and that will give me this, okay? And that there you have to replace X by Y, which is what I've done here. Y, then what you get as a weakest precondition is Y is equal to Y naught, Z is equal to X naught. And similarly, then I'll take that to push it back through C11, and that's what this thing is doing. So this one is the same as this one. Okay? Then that is pushed across Z is equal to X. And when I, so as Z is replaced by X, so I get Y is equal to Y naught and X is equal to X naught. Now with these two, and using the sequential composition rule over C11 and C12, which is what, I had recall the sequential composition rule, which is this, okay? And that's what I've used to get, I'm used to do this, these two. And then I compose this with that because the entire program is the composition of C1 and C2. So I'll have to apply another instantiation of the sequential composition because there are, so because C1 you get by composing these two things. So then what I will do is I will use the sequential composition on, this and, C2 to now get this entire thing, okay, over C1 and C2 to get, this one, okay, which is not exactly the same as, so see the precondition that you get as a result of pushing it all the way back is equivalent, but not identical to this. As you can see, this has X equal to Y naught, Y is equal to Y naught and X equal to X naught, but this one has it in the opposite direction. And it is in those kinds here, it is trivial, okay? You get by the commutativity, and there, that's when you will have to use the consequence rule when your the real assumption that you start the entire program with is not identical to the result of pushing the predicate backwards. Okay, and so that's when you have to use. Okay, so as you can see here in this, so this is what is called a Hoare proof. Okay, so because every thing here is a triple, and every triple is obtained from the previous set of triples. Every new triple in this tree is obtained by applying an inference rule. Okay, and that's so that's how you get it. In this case, we use the assignment rule, backward assignment rule, and the sequential composition rule to push the whole thing backwards. And finally, we used the consequence rule to show that the thing can be pushed. Now, discharging, as you can see, once you get the pushing the, applying the, pushing the predicates backwards or forwards is simple formula transformations, which can be done in a very syntactic fashion. But eventually checking these kinds of things, okay? These kinds of formulas, that is real, you need to use, something like an SMT solver for doing it, because there you will have to check the actual validity of these, formulas, okay? And, so that's why these proofs have two, automating these Hoare proofs, contains two parts. One is application of the inference rules can be done mechanically, okay, via pretty much substitutions. But applying the consequence rule will involve showing some actual validity of formulas for which you will have to use SMT formulas. Okay. Now, I think I'll stop here. I can take any questions you may have. Okay, and I will continue with this on Thursday. Okay, and use the tutorial to finish up this thing. And I think this is, I wanted to show forward proof as well, but I think I'll stop here because there have been a lot of details for you to digest. So I'll stop here and take any questions that you may have. Any questions? Okay. In which case, I will see you on Thursday at 5 o'clock. Yeah.
Yeah. Thank you.